there are functions out there whose limits give some particularly interesting behavior. For example, the function sine of 1 over x, when x is approaching 0, the limit does not exist. We're looking at a table of values that we can use to estimate the limit. On the left, we can see the x values that are approaching 0, and we can look and see in the function outputs that there's no trend. We're bouncing between positive and negative values. This is not a trend-producing behavior here. And if you don't trust it, you can always add more rows to this table, even closer to x equals 0, and you'll see that it still produces an oscillating behavior, bouncing between positives and negatives and positives and negatives. It never settles down on a particular value. Same thing with the right-hand side. We pick x values that are just right of 0, plug them into our function, and we cannot find a trend. So this function has a characteristic that we call uncontrollable oscillation. It's bouncing back and forth rapidly. We're taking very tiny steps in x, and we're making jumps in our function output values rather than small incremental changes in the outputs. Also, piecewise functions can be a little bit tricky when you're trying to find a limit at that transition point between the function definition. For this function f of x, we have a piecewise definition which transitions at the x value 2. If we pick smaller values of x, so smaller than 2, we get x plus 1 as our definition. But if we pick 2 or larger, we need to use x squared minus 4 as our function definition. So when we build our table, we'll make sure that for the left-hand limit, we'll use x plus 1, and for the right-hand limit, we'll use x squared minus 4. We fill out our table using points that are very close to 2 on the left side, points that are very close to 2 on the right side, and then of course we look for the trend in the behavior. As x is approaching 2 from the left, our function outputs are tending towards 3. So the left-sided limit's equal to 3. As x is approaching 2 from the right, our function outputs are tending towards 0. Notice that the decimal value is getting smaller and smaller, and more zeros are appearing in this pattern. It's safe to say that our function outputs are tending towards 0, so our right-hand limit is equal to 0. And recall that if the left and the right-hand limits do not send you to the same location, then we can't generalize and talk about a two-sided limit. In this case, the two-sided limit would not exist. Now let's look at a rational function, which has a 0 in the denominator when we plug 0 in. So the function 1 over x, it is not defined at 0, but we might want to talk about the behavior as we get very, very close to 0. We can build a table of values to represent the left-sided limit and a table of values to represent the right-sided limit. And we notice that when we take a small step in x, we see a very large step in the function outputs. So notice that negative 0.1 and negative 0.1, those are very close together. But negative 10 and negative 100, those are not so close together. And the same thing is happening as we move down the table. Also, the same thing's happening in the table that represents the right-handed limits. Small steps in x, but huge steps in our function output. And if we graph our function, we can see that the function values are infinitely large or infinitely small if you're coming from the left. So our left-sided limit is going to negative infinity, our right-sided limit is going to positive infinity when we're talking about this function 1 over x. This function does have what we call a vertical asymptote right at the y-axis. When x is equal to 0, this function splits and follows the vertical asymptote, getting infinitely close but never being equal to that vertical asymptote.